we will use the EAX register to perform all the stack placements and calculations. Remember that all the instructions we use in this shellcode must result in an allowed character range. We'll use the first following set of instructions to zero out EAX in order to start with a clean slate. At first sight, it might be unclear how these instructions zero out EAX. However, let's take a closer look at these values. Let's take the first value and convert it to binary. And let's copy this number to a text file. Now let's take a look at the second number. And once again, convert it to binary. If we now add these two values, these two numbers, we should see that we end up with all zeros. So let's see if these instructions behave as expected. Now, since the value of EAX is already 0, we probably won't see much change. So allow me to artificially change this value for us to see the effects of these instructions. So we start the ANDing process, and then we take the second instruction, and look at that. Any value that might have been an EAX will now be zeroed out. Our next step is to locate our position in the stack. If we push ESP onto the stack and then pop it back into EAX, we will effectively hold the address of ESP in EAX. This will later allow us to make relative memory calculations for expanding our encoded payload. So let's quickly add those instructions. And let's execute them to see that they work as expected. So pushing the address of ESP onto the stack and then popping it back to EAX will have this effect. Now that we've located an address that is near to us on the stack, we want to get the stack aligned with the position of where we will decode our shellcode. We need to roughly estimate where our encoded shellcode ends, which is impossible to do ahead of time, so this stage is usually kept for last. However, we will assume that we know that our encoded shellcode will take up around 253 bytes. Let's try to get a better idea of this estimate by looking at the memory dump. Assuming that all of this space will be taken up by our encoded shellcode, we might want to give a few extra bytes for safety's sake and start decoding our shellcode around here. Since we'll be decoding a 32-byte egg hunter, this area should provide ample space for proper decoding. Before we continue, let's take a few minutes to fix up our exploit, adjust some buffer lengths, and insert the beginning of our egg hunter. Let's binary copy these bytes, and we'll use this as the beginning of our egg hunter shellcode. Let's start by clearing out these comments and beginning to write our egg hunter shellcode. Now we had our conditional jump here, which brings us 29 bytes into this buffer here. So let's align our egg hunter to this jump. And at this stage of exploit development, we might also want to fix our buffer lengths to avoid any miscalculations, as they can be very costly down the road. So let's quickly fix this buffer length here. And to add to this, we'll add the egg hunter and pad it with a fixed buffer. So let's add A's, and we'd like a total buffer of 360, and we'll be subtracting that from whatever length the egg hunter is at the time of execution. To add to this, we won't forget to finish the host header with a port, and with that we should be good to go. I'll quickly fix this typo here, and we'll send this buffer and continue writing our shellcode. Once again, we take the pop ret, we set up our conditional jump, we take the jump, and we land at the beginning of our encoded egg hunter shellcode. So picking up from where we previously left, once again, these few egg hunter instructions set up EAX to point to our current location on the stack. Let's take these instructions. And EAX now holds the value of ESP. Assuming our egg hunter will take up around 250 bytes in its encoded form, that means that all of this space will be used by it. We'd like to start it decoding itself at the following address. Right here. So let's put a breakpoint here. And what will happen is that our egg hunter will slowly be decoded from this address onwards. So let's go back to our shellcode. Let's see how we can manipulate the EAX register using only subtract commands to get it to point to this required address. Alright, so I've added the following instructions. Let's see what happens to EAX as we subtract these three values from it. Wonderful. So EAX actually points to where we want to start decoding our egg hunter shellcode. A short explanation about this calculation can be found in the lab guide. So now that we've set up EAX to point to the position in the stack where we want to decode our shellcode, we'd like to move our stack pointer to that address as we start carving out our shellcode in memory and placing it on the stack. We can do this using the following instructions. We'll push the value of EAX onto the stack and pop it back into ESP. Let's take those instructions. Wonderful. So ESP now points to the address of where our shellcode will start decoding. Now we are free to write our decoding shellcode. We will take the original 32-byte egg hunter shellcode and break it down to 8 sets of 4 bytes. We will then proceed to carve these bytes into the EAX register and then push them onto the stack. Let's quickly remind ourselves of what our original 32-byte egg hunter shellcode looks like. So in this example, the first 4 bytes we will write will be the last 4 bytes of the egg hunter shellcode. So essentially, we need to make EAX equal this number, and once it is, we can push this value onto the stack. We will then proceed to do this with each line until the shellcode is fully formed on the stack. Let's look at the assembly code required to do this. We start by zeroing out EAX and subtracting the following values from it. Let's look back at our egg hunter shellcode and notice that the value in EAX should be exactly equal to the last 4 bytes of our egg hunter. So once we've carved this value in memory using these 3 instructions, we will push this value that is stored in EAX onto the stack. And let's see what happens right here. Look at that. So that value was pushed on the stack. The stack is now located here, and these bytes have just materialized at the end of our decoding shellcode. So let's proceed and carve out the rest of our egg hunter bytes and see how our decoded egg hunter materializes at the end of our buffer. Alright, so this is the rest of our shellcode, and you'll notice that each bunch of instructions essentially decodes 4 bytes of our egg hunter. Let's continue decoding. Once again, we zero out EAX, we carve the next 4 bytes in our egg hunter and push it onto the stack. We do this again. And those are the last 4 bytes, or actually the first 4 bytes of our egg hunter. And all we need to do now is allow for execution to continue, and eventually we should be meeting our decoded egg hunter. Here it is. And no matter how many times I do this, this always seems like witchcraft to me. But basically, from here on, the exercise should be familiar to you. Let's quickly step over the egg hunter and see that the egg is successfully identified in memory and executed. So we'll run the egg hunter, and let's place a couple of strategic breakpoints here and here. And let's just see that our egg hunter works as it should. So there it is, scanning in memory. And now it's looking for both instances of our egg. The host machine CPU should probably be at 100% usage right now. We can watch this as the exploitation progresses. Wonderful. So apparently our egg has been found, and let's see what we have waiting for us in EDI. And that looks wonderful. That looks like our dummy shellcode. So it looks like our decoding has successfully completed, and all we have left to do now is to add a bind or reverse shell in this buffer space here. So let's write all these egg hunter bytes into our exploit and replace this dummy buffer with a bind shell.